All right, today we're going to be looking at derivatives, and this is our first big topic that we're going to be talking about. So we'll notice that limits are going to kind of transcend all of our topics throughout the year. And then the next chunk of the year is going to be derivatives, and then the last chunk will be related to integrals, and then we kind of have 2 units in the BC class that pull both of those together, which is really cool to end off the year. So remember back to the first class that we had, we talked about this tangent line problem. You guys did a really good job investigating this and trying to figure out what the instantaneous rate of change was on a curve. And that's really what we're going to talk about. And you guys do already have a really good theoretical understanding of what's going on. And you guys also used, a lot of you used the limit as h went to 0 of the difference quotient, because you remembered that idea that we talked about. Well, that was the derivative. You guys were finding the derivative. You were finding the equation, finding an equation that could represent the slope or the instantaneous rate of change on a curve at any given point, which is really cool. So let's just kind of back up a little bit to make sure we're totally good to go with where all of this is coming from. And then we'll dive into the formalities of what a derivative is and how it may appear. So welcome to calculus. So we have 2 things that we've talked about before. We've talked about the secant line, and right now what we're going to do, and again we did this in honors pre-calc as well, is to compare that secant line to the tangent line and what kind of the differences are and what the similarities are. So our secant line, right, starts like this. We have some curve. We're going to have the exact same curve over here. So we'll go like this. Ooh, similar. And our secant line says, well, I have some x value right here, right? And then h spaces later, I have some x plus h value. And my secant line is this line that goes from x to x plus h, right? And we said that we could find the slope of this line quite easily, and we call that the average rate of change. So we say, well, first of all, that h is representing this delta x. So there's a change in x right here that we call delta x that's equal to h. So remember, in some of these problems, you may see delta x in lieu of h. By all means, replace that delta x with an h if that's more comfortable for you. If you want to practice using delta x, you're also welcome to do that as well. So our average rate of change, or our AROC, that's also representing the slope of the secant line. So I'm going to say MSEC to represent secant, is going to be f of x plus h subtract f of x all over x plus h subtract x. So I just took this value right here is f of x. This value right here is f of x plus h. And I just took those 2 values, right? Subtracted y2 minus y1 over x2 minus x1, and that's the slope of my secant line. And that simplifies down to f of x plus h subtract f of x all over h. And we defined this in pre-calc as my difference quotient. All right. Conversely, we have a secant line. And remember how we talked about the secant line? What it's doing is taking this tangent line, and we're getting closer and closer. So if I'm able to, let's see if I can. We're really kind of taking this line, right? And we are moving this point so that it's closer and closer until ultimately we are approximating this value right there to make a tangent line. So notice that a tangent line is just going to touch at that one point, rather than our secant line, which went from one end to the other, right? It had all this function in between. It passed through 2 points. When we're talking about a tangent line, we're going to have just a singular point at f of x. And now we're letting that h go to 0. So we're just going to have this line that touches just at one point and then extends infinitely in either directions. And don't get me wrong, notice that yes, it does. It may pass through here again, just by happen chance, because of the way a function appears. But what's important is that it's not passing through at this point, it's just touching it and then moving on. So this now is my x value, and we're actually going to call that, I apologize, we're actually going to call that C for this definition. And as a result, this right here is my f of C. And now what we're talking about when we're talking about this slope of the tangent line is we're talking about an instantaneous rate of change. So our slope of a tangent line is synonymous with the instantaneous rate of change. Instantaneous. Which generally speaking, we're just going to call IROC. And so what we say for our tangent line, our definition, is that if f is defined on an open interval, containing C, and if the limit as h approaches 0 of the slope of the secant line, which equates to the limit as h approaches 0 of f of x plus h, subtract f of x, all over h, equals the slope, if that exists, then I'm gonna have to go to the next page to have enough room. The line that passes through C of f of C with slope m is the tangent line to the graph of f at the point C f of C. What this is saying is that if we're defining this value to be, as h approaches 0, to be some slope, right? And what you're going to see is this may not be a numeric, like solely numerical answer. Oftentimes this is going to be an expression that we then need to substitute in an x or a y value to figure out what the actual slope is. But if this limit exists and gives us some type of output, then we can calculate that instantaneous rate of change, or that slope at that given point of the tangent line, and then we'll be able to write an equation given that it passes through this point C comma f of C. So what we say here is that we now have, actually let me start on a new page, the derivative of a function. Yay! And I know some of you guys might not see it just yet, but as we progress, you should be able to make some type of connection between derivatives and some things that you saw in chemistry last year. So see if while we're doing derivatives, if you can think back to chemistry and start to think about how those two things, or how some topics in chemistry relate to actually derivatives of functions. Ms. Ham, and this year, if you're taking it, Ms. Chandler won't be able to go into derivatives because obviously it's a junior level course and it's not necessary for them to be able to explain that. But you were tasked with memorizing something in chemistry that actually has a mathematical backing. And if you had known the math behind it, you wouldn't have had to memorize. You could have just calculated using derivatives, which is pretty cool. So we'll see if anyone can come up with what that connection is. But our derivative of a function states that f prime of x, and I'll explain this notation in just a moment, is going to be equal to the limit as h approaches 0 of f of x plus h, subtract f of x, this is why we did so much with the difference quotient, all over h. So this is a big one. This is the definition of the derivative. So anytime on the test it says use the definition of a derivative, you are going through this process. This notation right here represents the first derivative, and we denote it by, we call it f prime of x, but it just means that I'm taking the first derivative. We could also write this as y prime, so that's pronounced y prime. That's also a way to represent the first derivative. Another way is dy dx. And the way that we can say dy dx, we also say the derivative of y with respect to x. And then lastly, we may see d dx of f of x. And that simply means the derivative of f with respect to x. And so all of these represent taking the first derivative. And we'll get into higher order derivatives later. But these all just talk about taking that first derivative. The reason why we have so many different is because Lagrange and Newton, I think I described this before, both discovered calculus around the same time, and they use different notations. And as a result, we've realized that in some situations it's easier to use like f of x or f prime of x. In other situations it's going to be easier to use y prime. So we really and additionally in other situations we're really going to use that dy dx. So we really like to be fluid and practice using all different forms because in different situations as you get to higher level math, certain forms are just more efficient to write with or explain the problem with a little bit more depth and clarity. So we really want to be fluid with all of them. All right, let's go ahead and do a practice problem. Let's determine dy dt, so the derivative of y with respect to t of the function y equals 2 over t. All right, so this is my f of x function. This is like f of x equals 2 over x. So I'm going to go ahead and say, well, dy dt equals the limit as h goes to 0, and I have to do f of t plus h subtract f of t all over h. I have the limit as h goes to 0. I'm going to sub in this t plus h for t over here. So I'm going to have 2 over t plus h subtract my original function, 2 over t, all over h. And this is why we did all that practice, simplifying limits algebraically, because we need to be able to take the derivative, and the derivative is not always going to be pretty. So I'm going to go ahead and I'm going to multiply this whole thing by my common denominator. That gives me the limit as h goes to 0. My t plus h's cancel out. I get 2t subtract 2 multiplied by t plus h, because in this instance my t's cancel out, all over ht times t plus h. And again, leave that denominator factored. Our goal is for this numerator to have just solely h in it, or something times h, so that we can cancel out those h's and get this h out of the denominator somehow. We're trying to isolate an h in the numerator somehow to be able to cancel that out. So now in my numerator, I have 2t subtract 2t, there we go, subtract 2h, all over h times, ht times t plus h. I'm going to move to the right just because I'm running out of room. Notice my 2 t's cancel, so I'm left with the limit as h approaches 0 of a negative 2h all over ht times t plus h. And now we see that these h's can cancel. So I now have the limit as h goes to 0 of -2 over t multiplied by t plus h. So now I can sub in h because I can sub in 0 for h and I'm good to go. I end up getting -2 over t squared, which means that dy dt equals -2 over t squared. So the derivative of this function is -2 over t squared. So what this expression tells me is that if I have this curve 2 over t, this rational function, if I wanted to find the instantaneous rate at any point on that curve, all I would have to sub in is that input, that t value or that x value. So for example, when t equals 1, I would find that the instantaneous rate of change or the slope of the tangent line at that point is going to be -2. And that would make sense because this function is going to look something like just a rational function with just like a different slope. And notice that at -1, I have this pretty, or at +1 rather, I would have a pretty steep negative slope. So getting a slope of -2 would make sense for that, right? As this number gets larger and as I start going over towards infinity, right? Let's say I put in 100 for t. Now I have a number that's pretty close to 0. And as we know with rational functions, this is asymptotic with my x-axis, right? And that's getting to a slope that would be pretty close to a flat horizontal line, which would be 0. So this slope is approaching 0 as t gets larger and larger, or gets more and more negative. But as it gets closer to 0, right, I'm getting numbers like 1/2 squared, 1/8 squared, 1/100th squared, which are then making this number very large, which is why my slope of my tangent lines are becoming almost vertical. All right, let's look at one more example. And in this example, we're actually going to find the slope of the tangent line at a given point, and then we'll look at Desmos afterwards just to kind of verify what's going on. All right, our last example is to find the slope of the tangent line of f of x equal to the square root of x at 1, 1. Yeah, we'll just do it at 1 point. Actually, let's do it at my other point at 4, 2. Find the slope of the tangent line of f of x equal to the square root of x at 4, 2, and then we're going to write the equation of the line. Okay, so let's start off. We want to find the slope of the tangent line. Slope of the tangent line is the same thing as instantaneous rate of change, is the same thing as finding the derivative. Those three expressions, words, are all synonymous. So if you hear any of them, again, slope of the tangent line, instantaneous rate of change, or derivative, they're all talking about the exact same thing. We just use different wordings for different types of problems. So I know that I need to find f prime of x. And that's going to be equal to the limit as h goes to 0 of the square root of x plus h, subtract the square root of x all over h. So I see that I have radicals, so I know in my head that means I have to go ahead and multiply by the conjugate. All right, I'm going to get x plus h subtract x all over the square root of x plus h plus the square root of x. That's going to now give me h, because these cancel out. Oh, sorry, the limit as h goes to 0 of h over the square root of x plus h plus the square root of x. I'm going to go ahead. What did I do wrong? Oh, I dropped my h. There we go. H there. So now I can cross cancel those. So I'm left with the limit as h goes to 0 of 1 over the square root of x plus h plus the square root of x. Well, now when I sub in 0, I get 1 over root x plus root x. Root x plus root x is like having two things of the same term, combining like terms. So I have 1 over 2 root x. This is my instantaneous rate of change. I can say that f prime of x equals 1 over 2 root x. So the derivative of this function is 1 over 2 root x. All right, the next part says we want to find it at the point 4, 2. Well, notice that my derivative does not depend at all on y, it only depends on x. So if this is part A, part B is wondering what is f prime of 4? So all we're going to do here is sub in 4 to our function. And we get 1/4, which means the slope of the tangent line when x equals 4 is going to be 1/4. The last part says write the equation of the tangent line. And the reason why I really want you to stick with point slope form and not slope intercept is for this reason. This is going to happen again and again and again, where we have a point and we have a slope. Why on earth would you use slope intercept form when you have the beautiful, lovely form of y minus y1 equals m times x subtract x1? It just fits so perfectly. We have y subtract 2 equals 1/4 multiplied by x subtract 4. And so this gives us that tangent line right there. All right, I'm going to go ahead and pull up Desmos and we'll see what this looks like. All right, so you see here that I have the square root of x graphed, and notice that part of the domain of the square root of x, so this is a continuous function, but part of its domain is that x can't be less than 0. It can be equal to 0, but not less than 0. So what I'm going to go ahead and show you first is what that tangent line looks like. So we calculated the slope of the tangent line to be 1/4 when x equals 4 and y equals 2. And notice that we have that tangent line right there. So there's this point right here that the two functions share at 4, 2. But other than that, we don't have any commonalities, right? It's just a straight linear function, and it's just tangential at that point. Notice now, let me get rid of both of these. This is the function. This is f prime of x. And I actually on Desmos could have just done this. And it would give me that function as well. And notice that it doesn't have a linear anything less than 0 because that's not the domain of my original function. So that derivative really depends a lot on the domain of the original function for what it's going to look like, because we can only put those x values in that are true for my original f of x. And so notice this looks somewhat rational, right? Because we have that square root in the denominator. But we could look at this function now and we could find any of those derivatives. We could find any of the slopes at a given point. So we could say, all right, well, what's f prime of 16? That's going to be 1/8? Yeah, 1/8, which makes sense. If we were to plug that in, we'd get 2 times the square root of 16 and we'd get 2 times 4, which is 8. So that derivative will literally give me the equation that will give me the slope or the instantaneous rate of change of that at that point for whatever x value I'm putting into the function, which is really awesome. So this function again gives us the slope at any value of x within my original function.